Hi, today I would like to discuss about the problem that I had the opportunity to do with a student of mine. It's for Physics 534 here in Montreal, Canada. It's from high school, secondary 5, Physics from Lauren Hill Academy. So the question was, we have all these, this has to do with optics. We have all these lenses here, these 6 lenses, and the question is which of them are converging and which are diverging. Just to give the answer, and then I will explain how we get it. The ones with green, like 1, 4, and 6, they are converging, and the rest with blue, 2, 3, and 5, they are diverging. Of course, 1 and 2, everybody knows that this here it's a converging lens, and this here is diverging. This is also a convex lens, and this is a concave lens. And it's any book of physics, high school you can see that. And then we have these 4, let's name them. This here it's a plain concave lens, and this here is plain convex lens, and these 2 here they're called meniscus, and this here is a meniscus, with a negative meniscus, and this here it's a positive meniscus, and that has to do with the fact that for a lens to be converging, its focal length has to be positive. So that's why this here, since it's converging, it's positive. Its focal length it's positive, and this here is negative. First of all, I believe that this problem for this age of students, it's a bit advanced, and students most probably will not be able to do it because there are 2 ways of doing this problem. The one is to do the ray diagram, which involves, if you want to be precise and do everything in detail, it involves a lot of work and requires a very good knowledge of geometry, which I think students in this particular group, secondary 5, they don't have. And the second is by using the math, because first of all, this here, it's what? It's a conceptual question. And as I said in my, in one of my former videos, the best way to answer a conceptual question in physics is to do the math. It doesn't matter that they're conceptual. You still can do the math and prove what the problem or question is asking. So, but in order to do that, that's how I will try to do. But again, this is beyond the scope of this, the students of this class, because first of all, the formula that I will use, which is called the lens markers equation, I haven't seen it in any material that has to do with this course, and I searched, trust me, I searched thoroughly, and I haven't seen anywhere this formula. I will try to use it and explain a little bit the formula. And then I will try to do it with the ray diagram, which is something that a student that takes this course knows how to do, but again, in order to prove it completely, it requires a lot of detail and a lot of knowledge of geometry, which I believe that this student group doesn't have. So, and I will only do, because as I said, this and this you can find it in any book, I will do this here and this here, because are, let's say, the most challenging. Like this is almost like this, and this is almost like this. So I will do one of them, one of each, and let's do it. Okay, first of all, what is the formula that I will be using? I said again, it's the length marker's equation. This is something that for any student in university physics, like introductory optics and waves physics, you can find this formula. So I believe this problem is more appropriate for this kind of students. So what is this equation here? This equation here is that 1 over f is equal with n minus 1 times 1 over r1 minus 1 over r2. Now, f is the focal length of the lens that we are talking about, n is the index of refraction of the lens, r1 is the radius of curvature of the first part of the lens that the object is, and I will explain you what I mean exactly. And then R2 is the radius of curvature of the second phase that the rays will go. So let me now use this formula here and to prove that this here it's a converging lens. To prove that the lens is converging, you have to prove that f is positive. So its focal length it's positive. So let's do it. Let me show you something. This here, let's try to draw it in the right way. I would try to do it here. Let's say we have one big circle, approximately like this, and then we have one smaller circle, approximately like this. Okay, so that's how you create this circle here. So now you see that the center of curvature of the bigger circle is here. So, and the radius of the bigger circle is this here, is the red one. Now, the radius of the center of curvature of the smaller circle, let's say it's approximately here. So, the radius of curvature of this circle is this here. So that's how you create this lens here, which again is called the positive meniscus. So now let's see why using this formula here we can prove that this here has positive F, focal length. So just to make sure here that we understand what we are doing, let's say this is the R2 and this here is the R1. Okay, so now this here, which is this here, okay, I mean it's a lens. So now R1 is the radius of curvature of the part of the lens which is closer to the object. So just to make sure, let's say the object can be anywhere. So let's say it's somewhere here. So now, in order to prove that this it's positive, like the F, I mean, we need to prove that the 1 over F is positive. So that means that we have to, because the 1 over F is equal with this, we have to prove that the right hand side of the equation is positive. And let's work a little bit in this equation here. If you put this under the same denominator, you will have R2 minus R1 over R1 times R2. And I mean, of course, this is equal with this. And we said that the n minus 1, we didn't say it, we would say it now. The n minus 1 it will be positive because then it's greater than 1. So that means that this here is the n minus 1 is positive. So if we can prove that this here is positive, that means that this here is a converging lens. The F of this part, because it's concave, and just let me tell you something. I mean, this has to do with the focal length, the radius of curvature of lenses, which is different than what it's valid with mirrors. Actually, it's vice versa. Because this here it's a concave lens. That means that R is negative. And of course, this here it's a concave lens, so again the R is negative. So that means that R1 and R2 are negative. So that means that R1 times R2 is positive. And now the R2 minus R1, it's okay. The R2 minus 1. Let's see if it's positive or negative. Now we said that R2, like the absolute value of the R2, it's, you see it here, it's smaller than the absolute value of R1. But because both of them they are negative, that means that this is, if here is 0 and this is R1, this is R2. So you see that in absolute values the R2 is smaller than the R1. But in actual numbers, the R1 is smaller than R2. And you see it here in the number line. So that means that R2 minus R1 is positive. So that means that because this is also positive and we said everything else it's positive, that means that this lens here has a positive focal length. So that means there is that is converging. Now let me tell you something interesting, something else which is also interesting. Let's say that the object, is not here, but it's somewhere here, like in this, somewhere here. So like, in other words, in the initial figure, let's say that the object is somewhere here. What I'm trying to tell you is that this here is converging. Doesn't matter which side we pick. And let me show you how we prove this. Let me tell you why. I mean, again, we have to prove that the 1 over f, so the 1 over f, which is equal with this here, is positive. Again, this here is positive because n is greater than 1, the index of refraction. So that means that this here it's greater than 0. So now let's see R1 and R2. What's going on with R1 and R2? Now you see that the object is closer to this surface. What is this surface here? This surface here is a convex surface. So that means that the F and accordingly the R2, and of course then it continues and it goes to this here, which is again a convex part. So that means that also the R1 are what? Because they are convex, that means that both of them they are greater than 0. So that means that now we are here. Let's see, we are somewhere here. So R2 is here and R1 is here. You see now that so again we said that the object now is closer to this part. So and again this part here and this part, they are both convex. So that means that the f, the focal length, and the radius of curvatures, they are positive. But now we said that here in the equation, in the first part of the equation, it goes to the r that is closer to the object. So that means that we have to put here the one which is closer has radius of curvature r2. And then we'll do the other one which has R1. So, and now, let's again, see why this here is positive. I mean, if we work this here, it will be R1 minus R2 over R2 times R1. So now you see that, I mean, like again, this is positive. Now this here is also positive because of course the R1 is greater than R2, so that means that all this product here is positive, which means that F is positive, so that means that this length again is converging. Doesn't matter if you put the object from this side or from this side. I will show you now why this length here is diverging. So this lens here, it's called plano. It's called plano concave. Now let's see why this here it's a diverging lens. So I mean, let's say that the center of curvature. I mean, let's of course start with the fact that the object is on this side. So let's say somewhere here is the object. So this is the object here. So let's say the center of curvature of this side is somewhere here. So that means that the R1 is this here. And now, what about the center of curvature of this flat area? So, I mean, the center of curvature of this flat area, it's of course at infinity, and that's why. And that's why the center of curvature of this is infinity. And of course, it doesn't matter if it's on this side or this side. So now let's, using again the formula, try to prove that this length here, it's diverging length. Just this here has to be R1, and this has to be R2. So this is R1, and this is R2. Okay, so, and let's start from the fact that that the object is on this side. So we have again to prove that this here it's, we have to find, to check if it's positive or negative. It will be negative, but let's see why. So again, this here is positive because, since again it's glass, the material, the n is greater than 1, so n minus 1 is positive. Now, the R1 is what? The R1, it's because this here it's a concave lens, the R1 is negative. This here is negative. So that means that all this quantity here, is negative. Since the R1 is negative, the 1 over R1 is negative. And now the R2 is this here. So that means that the 1 over R2, it's 0, or, its limit is 0, so we can assume that it's 0. So that means that it's a positive number, which is the n minus 1, times a negative number, which is the 1 over R1. So that means that the 1 over f is negative, which means that f is negative, which means that this here is diverging mirror. And let's do it also the other way around. What do I mean by other way around? It's like, let's assume, like in the previous case, that now the object is somewhere here. So now again you have to prove, you have to check, how much is this here, if it's positive or if it's negative. Again, this here is positive. Now we said that here it's always the radius of curvature of the part of the lens which is closer to the object. So we said that this here is the object. So that means that